Hello. The purpose of this video is to provide an overview of the standards, intended pacing, and sample instructional strategies for Unit 4, Building Fraction Understanding. In this portion of the video, we are going to review the AKS and Indicators of Achievement, or IOAs, for Unit 4. The AKS is the overarching knowledge and skills that students are expected to master. The IOAs are the learning objectives that allow students to demonstrate mastery of the AKS. The AKS and IOAs may not be taught in their entirety for the first time they appear in the instructional calendar. Some AKS and IOAs will appear multiple times throughout the year. In Chapter 2, we will look to see how the AKS and IOAs in this unit are placed in detail. This unit has two AKS. Under the AKS, you will find the Indicators of Achievement, or IOAs. You will also see that we have provided you with the state's coding at the end of the IOAs so that if you're looking up resources on the Georgia DOE website, you are able to find the state and IOA that is related to the GCPS IOA. With the first AKS, A3, students will describe fractions and perform operations with fractions to solve relevant mathematical problems using part-whole strategies and visual models. In this unit, we will only focus on two indicators of achievement to help students show mastery of AKS 3. The first IOA 3B focuses on comparing and ordering up to 3 fractions, including fractions greater than 1, with different numerators and/or different denominators by flexibly using a variety of tools and strategies. They will record these comparisons with greater than, less than, or equal to symbols and justify conclusions. This is an extension of the work of previous grades where students compared fractions less than 1. With IOA 3C, students build on the work from 4th grade with addition and subtraction of fractions with like denominators to now modeling and solving problems involving addition and subtraction of fractions and mixed numbers with unlike denominators. Students will find common denominators when adding and subtracting fractions and mixed numbers with unlike denominators using visual fraction models such as area models, number lines, etc. to build their understanding. This standard is as much about why common denominators are needed as it is about how to find common denominators. Students use benchmark fractions and previous understandings of equivalent fractions to estimate and assess the reasonableness of their answers. Finally, IOA 7B is revisited in this unit as students continue to explore mean distribution visually and conceptually. Students will ask questions and answer them based on gathered information, observations, and appropriate graphical displays to solve problems relevant to everyday life. Students will explore mean from both dot plots and line plots. The pacing guide is an example intended to model how instruction of the AKS and IOAs in each unit may be facilitated, but teachers should design pacing to be responsive to the learning needs of your students. Let's look at the recommended pacing for Unit 4. Unit 4 has a suggested pacing of about 4 weeks. There are 23 given days of instruction on the pacing guide, including the Unit 4 assessment. Along with suggested pacing, you will see the AKS and IOAs for Unit 4. Take note of the bullets on the left side of the pacing guide. These show the learning progression of the AKS and IOAs for each unit and suggested manipulatives and tools. For Unit 4, you will need fraction tiles, fraction circles, and fraction squares. Unit 4 opens with 6 given instructional days for IOA 3B. comparing and ordering all types of fractions, including fractions less than 1 and greater than 1. This includes mixed numbers and improper fractions. The first lesson introduces comparisons using benchmark fractions and fraction tiles. Students will use benchmark fractions to compare fractions greater than 1 with unlike denominators. The learning progression will then move to representational visual fraction models with a continued focus on using benchmark fractions to estimate when making comparisons. The progression then introduces a linear model, number lines, before student progresses to abstract thinking. The extent of this IOA is comparing and ordering up to 3 fractions. Ordering fractions is anchored in the work students will do when comparing fractions. We compare fractions to order fractions. Please note that students should be able to justify comparisons throughout this learning progression. The remainder of Unit 4 will focus on IOA 3C, in which students solve relevant problems with adding and subtracting fractions and mixed numbers with unlike denominators. We begin with students adding fractions with unlike denominators concretely using fraction tiles on the first day, to doing the same thing with subtraction of fractions with unlike denominators the second day. By day 3, the progression will present lessons with both operations. This process will repeat once with adding and subtracting of mixed numbers is introduced. In subtraction situations, students will rename or regroup mixed numbers. Just as with comparing and ordering fractions, concrete models will include fraction tiles. Representational models will include fraction tile drawings, area models, and number lines. At the abstract level, students apply their understanding of equivalent fractions to rewrite fractions in an equivalent form to find common denominators. IOA 7B is revisited toward the end of Unit 4 with 2 given instructional days. Students will generate a statistical investigative question, collect specific measurement data, represent the data in a graphical display, in this case, line plots, and then interpret the data. Students will also answer relevant questions from the graphical display and then analyze the shape of the data in the process of exploring mean visually and conceptually. Measurement data will include fractions and mixed numbers with unlike denominators. On the right side of the pacing guide, you will notice a number of provided resources aligned to the bullets on the left side of the pacing guide. Throughout the pacing guide, you will notice different types of lessons: traditional teacher-directed lessons, and also task-based learning. For days where task-based lessons are provided, you will see a blurb above the linked lesson. Additionally, you will see resources that have been pulled from the adopted Georgia Reveal curriculum resource for 5th grade. These resources are not directly linked and can be accessed via GCPS portal. You will see examples of lessons that have been adapted from the Georgia Reveal components. Resources from the Georgia DOE have also been adapted and linked in the pacing guide. Some Georgia DOE resources have been directly linked. The Analyzing the Standards documents, or ATS, provide teachers with an overview of specific instructional strategies progressing from concrete to representational to abstract. The ATS for each IOA is linked to the pacing guide at the beginning of each unit. These can also be found on unit pages on eComm. You may also notice that the ATS has been linked to the top of each lesson plan provided on the pacing guide. Learning progression for Unit 5 is not linear. There will be times where you might need to connect back to concrete models when exploring representational and abstract strategies. This is especially true of adding and subtracting fractions and mixed numbers. I'll explain more about that later. For now, let's talk about IOA 3B. Students have had prior experience in 3rd and 4th grades comparing two fractions less than 1. In 5th grade, we're going to use this learning to now compare and order any fraction, including fractions greater than 1. This means that students will experience comparing and ordering up to 3 proper and improper fractions, as well as mixed numbers. Students are expected to order these 3 fractions symbolically. In this video, I will model using benchmark numbers with fraction tiles, number lines, and equivalent fractions to compare and order fractions greater than 1 using the same scenario. Here's our scenario. Jay challenged his little sister Lauren to a bike riding contest. They were supposed to ride their bikes for 2 miles, but they both stopped short of the goal. Now they are arguing about who rode their bike farther. JR rode his bike 1 1/3 miles, and Lauren rode her bike 1 3/4 miles. Who rode their bike farther? In this first lesson, teachers begin by modeling how to compare 2 fractions greater than 1. Students will then have an opportunity to compare a third distance to these 2 previous distances in the active engagement. It is important to start with concrete models like fraction tiles to build a strong fraction sense foundation. I'll model using fraction tiles now as I think through this situation. I know that 2 siblings are having a bike riding contest. They had a goal of 2 miles, but neither of them reached that goal. So I'll represent the original goal using 2 whole fraction tiles, mile 1 and mile 2. Also know that both siblings rode at least 1 mile. However, neither one reached the 2-mile mark. I have to determine who was closer to reaching that 2-mile mark. To do this, I will consider how close each of the rides were to the 1-mile mark, the 1.5-mile mark, and the 2-mile marks. These are my benchmarks. I have 1 mile represented and 2 miles represented. I'll use my half fraction tile to represent 1 1/2 miles. So I want to represent JR's distance. He rode his bike 1 1/3 miles. Now, I can clearly see that JR did not reach the 1.5 mile mark. He was actually closer to the 1 mile mark than he was the 2 mile mark. So now I want to think about Lauren's ride. Her ride was 1 3/4 miles. I can clearly see that not only did Lauren ride to a 1.5 mile, the 1.5 mile mark, but she rode past it. And I know this because 1.5 mile takes up the same amount of space as 1 2/4 miles. So my question asked me who rode their bike farther. Lauren did because she rode closer to the 2 mile mark than JR did. Now, remember I said that students will now have an opportunity to compare a third distance in the active engagement. Here is the next part. JR was not happy that he lost to his little sister, so he challenged himself to ride his bike farther than she did. This time, he rode his bike 1 5/8 miles. Did he ride his bike farther than Lauren? Order these distances, the distances of Lauren's ride and both of JR's rides from shortest to farthest. So again, we have these two distances represented. We need to represent JR's second ride of 1 5/8 miles. And then we're going to anchor that in comparing it to our benchmarks so that we get our students acclimated to doing the same. So now we have JR's second ride represented. I can see that for his second ride, JR actually made it past the 1.5 mile benchmark, because 1.5 miles is equivalent to 1 4/8 miles, and he rode 1 5/8 miles. Now, the question asks us, did JR ride his bike farther than Lauren? So while he did ride it past the 1.5 mile benchmark, he still didn't get as close as Lauren did to the 2 mile benchmark. So he did not. The question also asks us to order the three distances from shortest to the farthest ride. Now, clearly we can see that JR's first ride was the shortest because it was actually closer to the 1 mile mark than it was the 2 mile mark. So that was our first ride, the shortest ride. Now, we know that the second ride, JR's second ride, was longer than the first ride, but not longer than Lauren. So I'm just going to go ahead and move his up, his second ride up. That leaves Lauren ride as the longest ride, or the fact that she traveled farthest. This shows us clearly the length of the rides, with the shortest being first. Now, remember, I also said that students will have to write or order order the fractions symbolically. So this helps kids to really see the shortest distance. We can see that the shortest distance was 1 1/3 miles. That distance is less than JR's second ride of 1 5/8 miles. And then that distance of 1 5/8 miles is less than 1 3/4 miles. So our comparison statement is 1 1/3 miles is less than 1 5/8 miles, which is less than 1 3/4 miles. Now I'll model ordering fractions at the representational phase using a number line. So with number lines, organization can be an issue. I'll talk through how we can be proactive about that as I order the fractions from the previous scenario. I have my distances recorded, and I want to use benchmarks to help me structure my number lines. When plotting number lines, when plotting multiple fractions on multiple number lines, sometimes kids don't always start and end at the same place. And we know that this can skew their comparisons. So to kind of get ahead of that, we can model using a double, or in our case, since we have 3 fractions, a triple number line that starts and ends in the same place. So I know that I'm going to do that now. So I know that each ride was at least a mile long, and no ride was beyond the 2 miles because no one made it to the goal. So I'm going to use those as my starting and ending points because each of those rides fall between those 2 points. And again, I want to compare each of those rides to those same benchmarks of 1 mile, 1.5 miles, and 2 miles in order to determine who traveled farthest, because these are those benchmarks. So I'll go ahead and start a number line here. This is my 1 mile mark. I also suggest using a pencil to do this, but I wanted it to show up in our video. And this will be our 2 mile mark. And just a bit more. 2 mile mark. All right, and now I'm going to go ahead and just draw. Now that I have the same starting and ending point for each of these, I'm going to go ahead and connect them. This is for JR's first ride, Lauren's ride, and then JR's second ride, or ride B. All right, so I have my 1 mile marked and my 2 mile mark benchmark. Now I need to go ahead and show 1.5 miles on each one, because that'll give us a better picture of who rode their bike. So halfway between 1 and 2 miles is 1.5 miles. Another thing that students have trouble with is how to partition their lines. And so we need to remind them to look at their denominator, because this tells us how to partition our lines. Because JR's first ride, or ride A, was 1 1/3 miles long, we need to partition our number line into thirds. Go ahead and do that now. So this is about 1 1/3 miles. And I'll put my next one about here. That's 1 2/3 miles. And then we have the 3rd mile there. I'll go ahead and mark JR's ride with an X on the number line. Again, we can see that JR did not make, for his first ride, he did not reach that 1.5 mile mark. Now we'll go to Lauren's ride. Lauren rode 1 3/4 miles, so this tells us that we need to partition our line into fourths. We do that because our mile is already partitioned in half. We're going to take that each half and partition it into half to create fourths. So again, we have our 1.5 mile here. We're going to partition that in half, and then partition this half into half to create fourths. So now we have, this is 1 mile, 1 1/4 mile, 1 1/2, or an equivalent fraction would be 1 2/4 miles. And then 1 3/4 miles. And then we have 2. We'll mark Lauren's ride with an X in a different color. So again, we can clearly see that Lauren rode past the 1.5 mile mark, our 1 2/4 miles mark, and this will come in when we start talking about equivalent fractions. So she traveled farther than JR did, JR's first ride. So now we want to take a look finally at his second ride. We see that he rode 1 5/8 miles. That tells us to partition our line into eighths. We already have our halves. We're going to partition the line into fourths, each half into half to create fourths, and then partition those fourths into halves to create eighths. Each line into fourths, and then partition those fourths in half to create eighths. So this is 1 1/8 mile, 1 2/8 mile, or 1/4, 1 3/8 miles, 1 1/2, or 1 4/8 miles, 1 and 5/8 miles, 1 and 6/8 miles, 1 and 7/8 miles, and then 1 and 8/8 miles, or 2 miles. Now I'm going to represent JR's second rod, which was 1 and 5/8 miles. Again, we can see that JR rode his bike beyond the 1.5, 1 and 4/8 benchmark, but he did not ride farther than Lauren did. So now, remember, our students have to order fractions symbolically. It's from, in this case, from shortest to farthest. So it's easy for students to see that JR's first ride of 1 and 1/3 miles was less than his second ride of 1 and 5/8 miles, which was also less than Lauren's ride of 1 and 3/4 miles. Had prior experience with equivalent fractions in previous grades. We have also referred to equivalent fractions as we've moved through the learning progression. We're going to use this learning now to compare and order the mixed numbers from our scenario abstractly. Here are our distances. Again, JR's first ride is 1 and 1/3 miles. Lauren's ride was 1 and 3/4 miles, and JR's second ride was 1 and 5/8 miles. We are to determine who rode their bike the farthest. We are also charged with ordering the numbers from the shortest ride to the longest ride. So I want to think about the benchmarks 1 and 1/2 miles and 2 miles to help me order. I'm going to use a chart to help me organize my thinking. First, I want to compare each of the distances to 1.5 miles. I'll record all distances that are equivalent to 1.5 miles here. All distances less than 1.5 miles in this column. And distances greater than 1.5 miles in this column. All right, so let's look at JR's first rod. We know that JR's first ride of 1 and 1/3 miles is less than 1.5 miles, so we'll record it here. We know that Lauren's ride of 1 and 3/4 miles is greater than 1.5 miles. We know this because 1.5 is equivalent to 1 and 2/4. And 1 and 3/4 is 1 unit greater than 1 and 2/4. So we'll record Lauren's ride in this category. All right, looking at JR's second ride, we see that it's 1 and 5/8 miles. We know that 1 and 5/8 miles is greater than 1.5 miles because 1.5 miles is equivalent to 1 and 4/8 miles. So 1 and 5/8 miles is 1 unit larger than or greater than 1 and 4/8 miles. So I'll record JR's second rod here. Again, we can clearly see that JR's first ride was the shortest because it was less than 1 and 1/2 miles. However, his second ride and Lauren's ride were both greater than 1.5 miles. So now I want to think about how close each of those rides are to the 2-mile goal benchmark. I'll just think about how close they are to 2 miles. I know that 1 and 3/4 miles is 1/4 mile away from 2 miles, and that 1 5/8 miles is 3/8 miles from 2 miles. I know this because 1 3/4 plus 1 1/4 is equal to 2, and 1 5/8 plus 3/8 is equal to 2 as well. This is where students can connect their learning from 4th grade when they were adding and subtracting fractions with like denominators to determine how close a fraction is to a benchmark. So some students will clearly see that 1/4 is a shorter distance to the 2-mile mark, which makes Lawrence Ride the longest ride. But another strategy that you can use to help see which distance is closer is using equivalent fractions. So we can do this by using the multiplicative identity property. This just means that we can multiply a numerator and a denominator by the same number and the value not change of the fraction because we're just partitioning what's already there into smaller parts, into more parts. So what does this look like? If I have 1/4 and I multiply that by 1, that doesn't change the value of the fraction. It's still 1/4. So if I multiply the part of the fraction that part of the whole represented our numerator by 2, we get 2 parts. If I multiply the total amount of parts or our denominator by that same number of 2, we get 8 parts. So we know that 2/8 is equivalent to 1/4 because we multiplied it by 1. And all we are doing with that is just partitioning each of those parts into the same amount of parts. And remember, so students had experience generating equivalent fractions in various ways. This particular abstract strategy was introduced in 4th grade, but we'll also go through this progression again, generating equivalent fractions to add and subtract fractions with unlike denominators later in the unit. But as for now, with comparing, it's easier to compare 8s. We know this is the same. 1/4 is equal to 2/8. It's easier to compare 8s to 8s. So that may be easier for students to see that 2/8 is closer to 2 miles than 3/8. So Lawrence Ride was longer. Again, 1 1/3 miles, JR's first ride, was less than his second ride of 1 5/8 miles, which was also less than Lauren's ride of 1 3/4 miles. In 4th grade, students represented whole numbers and fractions as sum of fractions and recorded this work with an equation. They also added and subtracted fractions and mixed numbers with like denominators. With IOA 3C, we will build on this foundation to model and solve adding and subtracting fractions and mixed numbers with unlike denominators using a variety of strategies. It is important to first model situations with manipulatives and visual representations to continue to solidify fraction sense. Let's ensure that we're providing these opportunities for our students. After reading scenarios, students will have to decide if they should add or subtract, and in later units, multiply or divide. So it's imperative to model making sense of problems for your students. Another important thing to note as we add and subtract fractions is that we can help with fraction sense by remembering to estimate sums and differences to assess reasonableness of answers, just as we do with whole number operations. Now let's take a look at different strategies in the learning progression using the same problem. Here's our situation. Ansley and Joseph want to make s'mores. Ansley uses 3/4 of a bar of chocolate and Joseph uses 1/3 of a bar of chocolate. Ansley thinks that she uses 5/12 more of a chocolate bar to make her s'mores than Joseph because 3/4 minus 1/3 is equal to 5/12. Is Ansley's thinking correct? Why or why not? So to make sense of our problem, we know that two people are making s'mores and using different amounts of the same size candy bar. One of the people thinks that she knows how much more candy she uses than the other person. And we have to determine if her thinking is correct. So now is where we're going to start thinking about estimating. I see that Ansley uses a little less than a whole chocolate bar, and then Joseph uses less than half. We're trying to determine the difference in the two amounts. So 5/12 of a candy bar is a reasonable difference of less than one and then less than half. So now that we've kind of assessed the reasonableness of her answer, we do this to get kids to thinking about estimating before they go into their exact answers. We now need to find the exact answer. First, we're going to do this by using fraction tiles. What I want to do is represent the whole candy bar. It's important to let students know that we are, the candy bars are the same size. So this is our whole candy bar. Now I'm going to represent the amount of candy Ansley and Joseph use. So Ansley uses 3/4 of a candy bar. I want to show that she had the whole candy bar because that will come into play later. We're going to turn the fourth of amount that she doesn't use over. And now we're going to represent Joseph's third of a candy bar, and we'll turn over the amount to represent what he did not use. Right. So in order to determine the difference, we have to have the same size pieces or equivalent fractions. So this is where we'll create the equivalent fractions. To do this, we need to model showing a familiar process, a process that's very familiar to the students. They've had experiences exploring finding equivalent fractions with fraction tiles in 3rd and 4th grade. So we're going to model to remind them that we must use multiples of smaller unit fractions to cover that same area of the fraction that we're trying to find the equivalent fraction for. So we're going to start with, since we have thirds and fourths represented here, we need to find a fraction that is smaller, a unit fraction that is smaller, because we're going to be partitioning this fraction into smaller pieces. So that's why we would start with a smaller fraction. So just go through model showing them how the fractions are not great fractions to use, because they won't cover the same amount of space without overlapping or gaps. So if we use fifths, you can clearly see, and if you can't see that on there, I'll pull these back, that we can't use fifths because they don't cover the same amount of area. Great. All right, so then we'll go to sixths. And they can see that clearly, that if we use 2/6, that won't fit. So just go through the process. Fifth, sixth, we don't have sevenths. Now, here's the thing about eighths. Eighths will, as we know, will work for fourths. But then we have to test out those eighths for thirds. So we'll see that eighths will not work for thirds. All right, so eventually you'll keep going. You can go on to 10th, but we use 12ths. So we're trying to find equivalent fractions, and we do that by finding equal size pieces. So we see that 3/12, excuse me, yes, 3/12 is equivalent to 1/4. So if 3/12 is equal to 1/4, we need to do that for the other 2/4. All right, to represent Ansley's chocolate bar. And now we know that 4/12 is equal to 1/3 for Joseph's. So now that we have the same size pieces represented, we can clearly see the difference in the candy bars. So again, here's Ansley. Ansley has 1/12, 2/12, 3/12, 4/12, 5/12, 6/12, 7/12, 8/12, 9/12 is equal to 3/4. And then we have 1/12, 2/12, 3/12, 4/12 for Joseph. So we're going to write that equation down. So we have 9/12 minus 4/12 is equal to the difference in the two candy bars of 1/12, 2/12, 3/12, 4/12, 5/12. So to answer our question, is Ansley's thinking correct? Yes, Ansley's thinking is correct because 3/4 is equivalent to 9/12, and 1/3 is equivalent to 4/12, and 9/12 minus 4/12 is equal to 5/12. So the difference of the candy bars is 5/12. So now let's take this same situation and draw a linear model. We know that organization can be a problem when drawing area models. So we're going to draw a large rectangle and partition it into thirds to represent 3 holes. The one hole to refer to the whole candy bar, and then both amounts of candy. The whole. And then this will represent Ansley's amount of chocolate used, which is 3/4. And then this will represent Joseph's amount of chocolate used to make his s'mores. Now, just like our number lines, we know that our denominator tells us how to partition our model. So because Ansley used 3/4 amount of chocolate of a bar, we need to partition this whole candy bar into fourths. So I'll partition it in half, and then I'll partition each half into half to create fourths. Now I need to represent 3/4. 1/4. 2/4. 3/4. And remember, this last fourth represents the fourth that we had turned down because in our fraction with our fraction tiles, because Ansley only used 3/4. Now we need to represent Joseph's. Because Joseph ate or used 1/3 a candy bar, we would need to partition his line or his whole into thirds. About there. And there, and then we need to shade in 1/3. The DOE states that a strategy to be used when adding and subtracting, unlike denominators, is to generate equivalent fractions by partitioning using the denominators given in the situation. So we would partition our fourths that represent Ansley's candy bar into thirds. We'll do that. Partition this into thirds. And we need to make sure that we're partitioning the entire whole. This helps us determine what our denominator is. So if we count up each part in the whole, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, we have twelfths. And then we need to count up the parts represented, 1/12, 2/12, 3/12, 4/12, 5/12, 6/12, 7/12, 8/12, 9/12. We can see that 3/4 is equivalent to 9/12. It takes up the same amount of space. Now we need to partition our thirds into fourths. So again, I'll partition each third in half and then partition the halves into half. And then each half into half. And we have to do the entire whole. So again, in half. And then each half into half. We need to count up each part to determine the whole. And then the denominator, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, we have twelfths. And how much is represented is 1/12, 2/12, 3/12, 4/12. So now we have 1/3 is equal to 4/12. Now we can clearly see the difference in the two amounts because we have the same sized parts. So the difference in Ansley's amount and Joseph's amount is 1/12, 2/12, 3/12, 4/12, 5/12. So 9/12 chocolate minus 4/12 chocolate, the difference in the two amounts is 5/12. So Ansley's thinking is correct. In this stage, we begin to connect what we are doing or what we are representing visually to what is happening abstractly. So after drawing the visual model, we can pair this situation with the standard algorithm. However, students should use strategies that make the most sense and is most efficient to them. So continue to pair this abstract thinking that we're about to do until the end of the progression. So let's go ahead and connect using multiplicative identity property, which, as you remember from IOA 3B with comparing fractions, is just generating equivalent fractions by multiplying the numerator and the denominator by the same number. So we've already done that work with our visual model. So again, I'm going to write down those fractions. So 3/4 chocolate was Ansley's amount, and then Joseph had 1/3 of chocolate. Now, What we did here was we partitioned the fourth into thirds because we know that we didn't change, we didn't add anything to the amounts, we didn't shade anything extra. We just partitioned what was already there. So 3/4 is equal to 3/4, but we partitioned the whole by thirds into thirds. So we had a denominator of 12, or we created 12ths, and then the amount of parts that were represented were 9. So 9 of those 12ths are equivalent to 3/4. Now then we go to Joseph's amount. We partition Joseph's candy bar that were once partitioned into thirds into fourths. So took that 1/3 and we partitioned it into fourths, and we created 12ths, and the amount represented was 4. So now we have 9/12 and 4/12. Now we can see the difference in the two amounts. 9/12 minus 4/12 is 5/12. So again, Ansley's thinking was correct. Make sure you provide multiple opportunities to connect this abstract thinking to visual models. So which strategy? In mathematics, the emphasis is on the reasoning and thinking about the quantities within mathematical context. Specific mathematics strategies for teaching and learning are not mandated by the Georgia Department of Education or assessed on state or federally mandated tests. Students may solve problems in different ways and have the flexibility to choose a mathematical strategy that allows them to make sense of and strategically solve problems using efficient methods that are the most comfortable for and make sense to them. It is critical that teachers and parents remain partners to help each child grow to become a mathematically literate citizen. These standards preserve and affirm local control and flexibility. Thank you for watching. Please use your phone to scan the QR code on the screen or go to the website shown to get your completion credit in PD&E.